let's now start our next lecture on the isoparametric mapping. This is what we will cover in this lecture. So we're going to talk about mapping the geometry, as I discussed many times earlier in the course. Whenever you use a finite element software out there, most likely this is going to be using some sort of isoparametric formulation, either linear, quadratic. But the idea is that you have some sort of canonical element or master element with its own coordinates, right? And so we are going to map the geometry to the actual physical element. And depending on how we map that geometry, we look at the order, the polynomial interpolation order of that mapping. We compare to the polynomial order that we use for interpolation of the shape functions, right? Like our field. And if those are equal, then we have an isoparametric formulation. So we will look at an isoparametric mapping. Of course, we start in 1D. And the main purpose of having some sort of mapping is to have quadrature rules, right? Because all those quadrature rules are normally not defined in the physical space, but in our canonical element. And then we will look at the mapping in higher dimensions. And we, of course, as usual, we are going to look at some examples. All right. So when we talk about our canonical element, at least in 1D, we are looking at this element, right? We have some coordinate here, C, that is basically between -1 and 1. Remember that all our integration rules are between -1 and 1, right? You can also define rules between 0 and 1. Those are also existing. You could define rules for any interval, but the ones that we normally use, Gauss quadrature rules, are defined between -1 and 1, right? And those are internal rules. You also have different types of rules. You can have Gauss-Lobato rules, where you also consider the ends of the interval, but normally people work with standard Gauss quadrature rules, and those are defined in this interval. So the idea is that if I want to map, so since this is my physical element, right? So notice here I have my xi, right? So that is the left node. This is xj, my right node. So the idea is that I have to devise some mapping that basically maps this coordinate here into that node and this coordinate here into that node. Well, of course, the more straightforward way to do this is just to use the shape functions that we have been using so far, but defining those shape functions in our master element, right? So if I take phi1 to be this shape function and phi2 to be that shape function, well, I can simply express the coordinate, the physical coordinate x, right, as some sort of linear combination of those two shape functions, right? So I'm going to take the first function phi, and I'm going to multiply that by my left coordinate xi, plus my other second shape function phi j, and I multiply that by my right coordinate xj, right? So as you can see here, obviously I have some linear interpolation between the two end coordinates of the node. So for instance, if I am at the middle, right at the middle, well, in that particular case, we are weighting both shape functions at 1/2, right? X is equal to 0 there. And so it's basically xi plus xj divided by 2. Very, very straightforward. Whenever I'm here, right, well, xi is equal to -1. So -1, this is going to be 2 divided by 2 is equal to 1. And this term goes to 0. And the same with the other one. So notice the way we are expressing in the end, we're expressing the coordinate. And you already see that it looks very familiar to our field, right? So if I represent the field linearly using these shape functions, then basically we get to the isoparametric mapping, as we will discuss. So in this particular case, we can have a straightforward inverse mapping, right? So it is very, very straightforward to just obtain the c coordinate as a function of my x coordinate, right? In this case, it's very straightforward to do this. One second, guys. Don't close it, okay? But that is normally not always the case, right? For instance, we will see that there are cases, for instance, in your quadrangular bilinear finite element. Now we have some sort of bilinear term, right? So we have a nonlinear term. The bilinear xy term is into the mapping, right? And so in order to get our c coordinate in canonical space, then we basically have to solve an inverse mapping that is a nonlinear mapping. And that is straightforward? No, it's not straightforward. we normally have to solve some sort of nonlinear equation in order to get our canonical coordinate. But for the linear case, we can have an inverse relationship that looks like this, right? C is 2x minus xi minus xj, and then in the denominator you have xj minus xi, which is the length of the element, right? Okay, so now that we understand that we are representing our geometry linearly, right? It makes no sense to represent this particular geometry differently, right? We don't gain anything by representing this quadratically, right? It's not like in 2D that you can have an edge and then that edge can be a curve, right? Here, it makes no sense to represent that geometry with a higher polynomial order than a linear order. And so for this particular case, if we represent the geometry in this form and then we represent our field in the same form, that is why we call it isoparametric. They both have the same parametrization. So iso means equal or the same. Okay? And so obviously this is not the only option. You could have also parametrizations that are subparametric or superparametric, right? And then we're always thinking about the geometry. If the geometry is interpolated at a higher degree, right, then this is called a superparametric formulation. If, on the other hand, you have the geometry interpolated with a lower polynomial, that is a subparametric interpolation. And for instance, can you give me perhaps one example of a subparametric formulation? We have also discussed this in the past. What would be an example of a subparametric formulation? Yeah, and then your geometry remains linear. So that's one case. Say your geometry is interpolated linearly, but then you approximate the field with quadratic or cubic polynomials. That is a subparametric formulation. And for instance, what we will see, that is the case when we go to PFAM, right? We said in PFAM, well, I want to keep my mesh fixed, and then I'm going to increase the polynomial interpolation order to an arbitrary degree that we want. But of course, in 1D, again, it makes absolutely no sense to increase the geometry interpolation order. So we keep that linear. And so since the field can be approximated at an arbitrary polynomial order, then that is, again, one example of a subparametric formulation, right? A superparametric formulation, you could think, for instance, of interpolating the field linearly and then somehow expressing the geometry with an exact function like a circle arc, or you could think of some NURBS representation of your geometry. So NURBS are what people use in CAD, right, computer-aided design. And so it is possible to use those interpolations as well. But superparametric formulations have some issues, right? There are some complications. Sometimes when you use a superparametric formulation, you cannot really even describe a rigid body mode. That if you, for instance, prescribe a rigid body rotation, you can get artificial stresses in your domain that, sometimes this is a problematic issue. So superparametric formulations are not so common. Normally, we keep it subparametric or isoparametric, which is the most common, and it is definitely the type of formulation that you're going to encounter when you grab a finite element software. Okay, so as we discussed, these are basically used for integration. So take this function, right? We want to integrate throughout the element this function f of x, right, in the physical element. Well, obviously, now that we're going to try to integrate and use quadrature rules that are defined in my canonical master element -1 and 1, right, then of course we have to do the transformation of coordinates. And so I'm going to transform that integral. So the limits of integration, as you see here, they change to -1 and 1. So my coordinate of integration is dxc. And then I have here the Jacobian of that transformation popping up. Right? It's very simple to see that dx is simply j dxc. And so that is a coordinate transformation that I'm going to create. Now, obviously, f is still being a function of x, the physical coordinate x. So if at some point that coordinate, physical coordinate, is a function also, like we had it earlier, a function of the shape functions that are defined on the canonical element, well, something has to be done to transform my canonical master or master element coordinate into my physical coordinate, right? So at the end, what we want is to evaluate this expression, right, at a set of specified quadrature integration points, Ci, right? And of course, as you know, those are well defined. They are actually defined in such a way that you can integrate exactly polynomials of certain degree. So as we discussed in 1D, these quadrature rules are defined so that n integration points integrate exactly a polynomial order of 2n minus 1, very well, right? And so we can say, well, I'm going to approximate this integral, and that's why I write here approximately equal, the sum of the number of Gauss points, I equals 1 to n gp, and then I'm going to evaluate the integrand at this location. This is my integration point, right? But again, since that integration point is still not the physical coordinate, I'm going to have to map that to the physical coordinate and then make the evaluation. And probably you saw this in the project already, right? We cannot evaluate our body force straight in our isoparametric space, but you have to compute the physical coordinate before you evaluate the body force or the force per unit length in the project, right? And so obviously the Jacobian of the transformation enters this expression, and that is a way to map the lengths of both elements. So physically, that's what it means. This is the determinant of my Jacobian matrix. This essentially represents the ratio between the lengths in the physical space and my canonical element, right? And so this here, this gamma, is the weight that is associated to that Gauss point. And of course, the higher the integration rule, the lower is going to be the weight that is assigned to each of those integration points, because at the end, of course, you want that all the weights sum up to 2, which is, you know, the length of the interval. Okay, and these are well known. So for instance, for 1D, you have these Gauss points. So if you take a 1-point quadrature rule, obviously you are evaluating that in the center of the element. So a 1-point quadrature rule integrates exactly a polynomial of degree 1, exactly. And you know, it's very straightforward to see that if in that interval you have some sort of linear function, well, obviously you need to evaluate that in the center, right? So that you more or less get the average value of the function in the interval, yeah, multiplied by the width of the interval. Okay, now notice that the weight that is assigned to that Gauss point is equal to 2, right? Now, if I take 2 integration points, these are the values, and now I assign a weight of 1 and 1, and so on. So these are well defined. Of course, in the slide, it makes no sense that I go beyond 3, because then the expressions get very, very complicated, or then I have to use many digits of precision, and then doesn't look so clean anymore, but you get the point. I mean, these are well defined, and they are tabulated. We don't have to think about them. In the code, actually, there is a function that is called grule. You probably saw that. And this gives you the integration full of arbitrary number of points, right? So you just pass as an argument the number of integration points that you want, and it returns all the points and their weights. So in a way, we're computing the quadrature rule as we go. Okay, well, we talked about this already. N quadrature points integrate exactly a polynomial of order 2ngp minus 1. But obviously here, notice, I forgot to say that, but I say approximately equal. That is going to become equal just in the case we're integrating a polynomial, right? And well, that happens most of the times, at least in 1D, in our finite element computations. When we go to higher dimensions, things become a little bit trickier, right? Because sometimes we don't integrate polynomials anymore. Sometimes we integrate rational functions, right? If you recall, well, we're going to see this later, but sometimes the Jacobian is actually not constant. So the Jacobian is a function of a coordinate, and so that may be complicating things, because you have the Jacobian on the numerator, but then you have twice the Jacobian in the denominator, right? And so we will see why that happens, and that may complicate things, because then you are no longer integrating a polynomial. Okay, so let's take a look at an example so that you can understand how this works. And I like this example because we did it without relying on the isoparametric formulation. So we actually computed already, if you recall, in the 1D elastostatics lecture, we computed the stiffness matrix for an element, right? And so we know that the element matrix that is associated with that element I is computed as the integral over, well, the length of the element, and then you have this Ki is the axial rigidity of the bar, right? So EA, and then you have the B transpose B. B was what? Higher?
The shape functions?
No, they're shape functions. This, what? Strain displacement matrix. Remember, B has derivatives of the shape functions, right? And is a matrix that we use to relate the strains and displacements. But recall that B is always going to be a function of X. So these ones have now derivatives of the shape functions, right, that are defined on the canonical element. But I don't care about the derivatives in the canonical element. I care about the derivatives in the physical element. So there's going to be some change rule there that is going to pop up, right? So let's take a look. Now, if I'm going to be carrying out the integral in the master element, my shape functions are straightforward, the same shape functions we looked at earlier, right? And the derivatives are constant, minus 1/2 and 1/2. And so since B, and this is what I was just saying, since B requires derivative with respect to the coordinate x, right, we apply the change rule. So then B, which is supposed to be d phi dx, but phi is defined with respect to c, now I have d phi dx dx. Of course, this is transposed, then d phi dx dx again. And notice that this guy here is actually the inverse of the Jacobian. That's why I was saying earlier that if I have the Jacobian as the numerator, suddenly this term pops up twice, and then I have 1 over the Jacobian in the end. And that is why when the Jacobian is no longer constant, right, then you may have a situation where you're no longer integrating a polynomial function. You may be integrating a rational function, okay? And so now we get into this whole expression. It looks kind of complicated, but it is really very, very straightforward because, again, this is the Jacobian, the Li, which is the length of the element divided by 2, but then I have this guy twice, right? And so all of this is constant. So the moment we carry out that integral, we get into the exact stiffness matrix as we had before, which is the infamous EA over L 1 minus 1 minus 1, 1 that we have seen forever, right? We have that expression. Of course, that holds as long as this guy here is constant, right? So we assume that we have a constant Young modulus and a constant area along the element, okay? So again, we obtain the same stiffness matrix. Okay, now let's move to higher dimensions. Let's see what happens when we look at the shape functions, and we start with the triangle and quadrangular elements. And it is actually not so difficult to create or to derive these shape functions, right? So the idea is, well, if I want my canonical element to look like this, right? So where I am, this is my master element space. So this is my first coordinate c, this is my second coordinate eta, right? So this is going to be my first node, c eta equals 0, and then this is going to be my second node, c equals 1, eta 0, and this is going to be my third node, which is c0 eta equals to 1, right? So you notice already that the area of this triangle is what in this coordinate space? 1/2, very well. And so if I want to create or basically decide what is the shape function that is associated with that node, all I have to do is to basically look at the functions that go through the other nodes. So in this particular case, there is this function here, c plus eta equals 1, right? And so if I just look at this function, that already gives me the shape function associated with that first node, because obviously the distance from this node to that line is equal to 0, the same here. And so if I take that, my first function is going to be 1 minus c minus eta. And you can very quickly test this, right? So when c and eta are equal to 0, I'm at this point. The value is equal to 1, right? When c is equal to 1, eta is equal to 0, I am at here. So 1 minus 1 is 0. When c is equal to 0, eta is equal to 1, I'm here, right? And that is also 0. So that is my first shake function. Okay, well, then if I want, now let's do it together, because now that we understand the principle, right, I just basically need to come up with the line that goes through the other nodes, right? So that their distance is 0. So if I want the shake function from this guy, right, I have to come up with a line that passes through these two nodes, and that is which line? Sorry? C. Who said C? Yeah. Right? So when c is equal to 0, I'm here, and notice that the values of these two is equal to 0. When c is equal to 1 is here. Well, conversely, when I want the shake function from that guy, what is the line that I need? Eta. So eta, this is the last shake function. And the nice thing about this very simple exercise is that we didn't have to do any scaling, because notice that we always want the value of the shake function at a node to be equal to 1. And it just happens that for this particular configuration, for this particular element, right, it just automatically happened that the shake functions were equal to 1 at the node, but that is sometimes no longer the case with other examples, and that is what we're going to do next. So, well, when you plot these functions, right, these are the way they look like. Of course, they are linear, right? And so that is the reason why this element is the so-called constant strain triangle, right? So what is constant? The strain is constant, right? That's why it's called the constant strain triangle. And if strain is constant, what else is constant?
Derivative?
Mm-hmm. If strain is constant, strain is already the derivative. What else is constant? Stress. As long as, of course, we assume that the elasticity tensor does not change inside the element, obviously we're talking about a constant state of stress. And so in the project, right, I also ask you to solve the second problem with 2D elements. And so at some point I ask you, well, compute the stress, right, at every element. Yeah, well, obviously if the stress is constant inside the element, you don't need to do much work, right? You just basically compute your strain displacement matrix, and then you multiply by your elasticity tensor, and that is going to be the value throughout the element, okay? Okay. Well, as we discussed, this function satisfy the so-called Kronecker delta property. Again, what was the Kronecker delta property? Function is equal to 1 at the node and 0 at every other node. Therefore, the Kronecker delta property. All right. For the bilinear quadrangle, things are not so easy anymore. So let's assume that now this is going to be my first node, so -1, -1. So this element is defined in -1, -1, and +1, +1, okay? So this is my first node, this is my second node, my third node, and my fourth node. And so now, if I want to basically come up with the shake function, this guy here, right, then I have to look at lines that go through the other 3 nodes. So I have to look at this line here and this line here, right? That's why for the first function, if I take y minus c and I take this line, right, 1 minus eta, then I get this guy here. But there is a little caveat here, because if I don't do anything, so let's say this c is not there, right? If I don't do anything, when I am at this point, right, what is the value of that function? 1 minus c and 1 minus eta?
4.
Is equal to 4. And so now I understand that c has to be 1/4 if I want to force the shake function to be equal to 1 at that point, right? And this is basically what this sentence here is saying. So with the constant c equals 1/4, then I satisfy that phi1 at c1 is equal to 1. And obviously, every other node, that function is going to be equal to 0, right? All right, well, the same the same way we can also do the other shape functions. It's very straightforward. So when I'm here, right, I have to take a look at this line and that line. And then when I'm here, I have to look at this line and that line. And finally, when I'm here, I have to look at this line and that line. And then we get in this compact form. So this is basically all shape functions, right? In one equation, it's just that I'm going to be using this ci and then eta I, and those are basically the coordinates of the node, right, that are going to be corresponding to the function. Okay, these are the way they look, and these are actually mathematically exact, right? So I actually plotted this in this nice PGF plots library that I shared with you already. You can plot these functions as well, and you can see the curvature, right? You can see the effect of this bilinear term, right? So because now we have a bilinear term, then I'm going to ask you, how do you think my strain displacement matrix is going to look like? Is it going to be constant? Not anymore. I'm going to have some terms that are non-constant in that matrix. And so, again, if I am mapping the geometry, notice that this is the geometry mapping, right? So the master element gets mapped into the physical element, right, in the physical space, right? Obviously, there is a direct mapping that is very straightforward, the same way we wrote every single equation so far. So my x is going to be equal to the sum I is equal to 1 to 4 of phi xi being the coordinates of the nodes in the physical space. That is the way we do the geometry, the mapping of the geometry. But now when I want to go back, the inverse mapping is not so straightforward anymore. So normally, when we have this case, if for some reason, and there are situations where we actually need to find out what is the physical coordinate that corresponds to a given master element coordinate, right, then we have to solve a nonlinear equation. So we use Newton's method to iteratively, starting from a given point, let's say I start here, and then it converges, let's say, to my location C in master element coordinate. Okay. So that's it for the isoparametric mapping. This was more or less a short lecture, although it took 27 minutes. But let me ask you, do you have any questions regarding this lecture? Straightforward? Pretty much, no? Yeah? All right. We'll stop, and then after the break, we're going to start with the B version of the finite element method in 1D, which is one of the lectures I like the most.